So, most of the part of the capacitor we have completed. So, in today's class we will talk about dielectrics, their properties and dielectric constant, and we will find the way how to find out capacitance when dielectrics are involved in a different situations. So, let us start. So, dielectrics, what are dielectrics? They are insulating material. When subjected to external electric field, the molecule inside will try to align themselves along the direction of field. So, dielectrics are basically just insulators. So, a dielectric material is an electrical insulator that can be polarized by an application of electric field. So, when you subject electric field to dielectric, then the polarization will come into picture. When a dielectric material is placed in electric field, the electric charge do not flow through the material. So, like in case of conductor, when we apply field, so there will be a transient state, in that electrons start drifting, we have seen in conductor, and then electrostatic condition, they will occupy the space in such a way so that at each and every point inside the net electric field has to be 0, right. But that is not the situation in case of dielectric material, right. So, in dielectric material, charge cannot flow through as they were doing in conductors. So, what happens when you apply external field, charge get relatively shifted from its initial position. So, there is an average displacement, and because of that dielectric gets polarized, right. So, we will learn how that happens. So, basically dielectrics are divided into two categories, polar and non-polar. So, we have two types of dielectric, one is called polar, another is called non-polar, right. What are polar dielectrics? So, as we have seen in case of water molecule, that the shared electron here, because of high electron affinity of oxygen, they get shifted towards oxygen, right. So, oxygen will have slightly negative and this hydrogen will have slightly positive charge. So, shared electron get shifted. So, charge center, as you can see, positive charge center and this negative charge center, they are not coinciding. So, initially there is dipole moment in the molecule, and we have seen the direction of dipole moment from negative to positive, right. So, polar molecules are those molecules in which center of positive charge does not coincide with center of negative charge. For example, HCl molecule, same as water molecule, we have seen HCl molecule, hydrogen and this chlorine. As the electron affinity of chlorine is more, the shared electron will shift towards chlorine and it will be slightly negative and this will be slightly positive. So, this will have dipole moment, right. So, water molecule, NH3, these are the example of polar molecules, right. So, initially they have some dipole moment, their positive charge center and negative charge centers are not coinciding, right. Then comes what happens when these materials are subjected to external electric field. In the absence of electric field, what happens? These all dipoles will be randomly aligned. As you can see that this is this way and this is this way and this is this way, right. See, all will be randomly aligned, and the net effect, if I see, or if I want to calculate net dipole moment of this whole thing, that will be coming 0 because all are randomly aligned, they are in different direction. So, in the absence of external field, the permanent dipole of the molecule orientation is in the random direction, right. Hence, the net dipole moment of the material, if I take, is coming 0. But when it is subjected to external field, when I place the whole dielectric in some external field, then they start aligning themselves along the direction of field. So, this is what happens. So, if I apply external field this way, so this way field is applied, external field is applied this way. So, what happens that all these dipole, they start aligning themselves along the direction of external field, right. Due to thermal agitation and all, the alignment won't be perfect. For ideal situation we take alignment perfect, but practically because of thermal agitation this alignment won't be perfect. You can see that all are not exactly straight, so they are still not perfectly aligned, right, and that is due to thermal agitation. So, when an external field is applied, the dipole start aligning themselves in a regular fashion, and hence the dipole moment is induced. So, this material now will have net dipole moment in this direction, right, along the direction of field, and complete alignment is not possible due to thermal agitation, as I told you that these all are vibrating because of thermal agitation, they will not be perfectly aligned along the direction of field. Now comes non-polar molecules. So, non-polar molecule if I take oxygen, then because both are having same electron affinity, the shear electron won't shift towards any of the oxygen, and these type of molecule come under category of non-polar molecule, right. So, the molecule in which the center of positive charge coincides with center of negative charge, the molecule is said to be non-polar molecule, and examples are nitrogen, oxygen. So, these are the example of non-polar molecule. There exists a symmetry, so you can see that there exists a symmetry, and their positive charge center and negative charge center will coincide, and the net dipole moment won't be there, and this comes in the category of non-polar dielectric. So, initially what happens that shared electron and the positive charge here, they will be such that positive charge center and negative charge center, they will coincide. So, initially they are coinciding, they are non-polar in nature, but when place in external field, if I place the whole thing in external field, then what happens that positive charge start slightly shifting along the direction of field. So, I have applied external field, and you can see that this positive charge will get shifted this way, and these negative charge will shift opposite to the field. So, due to this shifting, the positive charge center and negative charge center, now they are not coinciding, right. So, when subjected to external field, what happens that as positive charge is pushed towards field and the negative charge will be opposite to the field, due to separation of effective charge center, the dipole is formed. So, initially there is no dipole because their positive charge center and negative charge centers were coinciding, but when it is subjected to external field, then they develop dipole moment. In the previous case, we were talking about polar dielectrics. Initially they all had the dipole moment, but the problem was they were randomly aligned, right. So, net dipole moment was 0. So, every molecule was having dipole moment, but as it was randomly aligned, so net dipole moment of the material was 0, and when you allow field, then all try to align themselves along the field, and there is a net dipole moment. In this situation, initially there is no net dipole moment, but initially every molecule won't have any dipole moment, but when subjected to field, dipole moment is produced, right. So, this is the basic difference between non-polar and polar dielectrics. I hope it is clear. Now, so here we defined a physical parameter called dielectric constant. How it is defined? Let us see. So, this is the dielectric which is placed in an external field. To create an external field, I took two plates, one is positively charged, another is negatively charged. So, because of this one, because of these charges, there will be field, right, this E naught. So, E naught will be something like this, E naught, this is E naught, right. So, this way there will be field in a space due to charges on two plates of capacitor. This is plus Q charge and this is minus Q charge, and we know what is the magnitude of this field, right. Now, as you can see that all dipole align themselves along the direction of field, all dipole will align themselves along the direction of field. So, this will be negative, this will be positive, similarly this negative, this positive, this way, right. If I just look at this part, for far away point or large distance, the effect of these two will cancel each other. Similarly, effect of these two will cancel each other, effect of these two will get cancelled. So, all this combination they will cancel each other for far away point, right. So, what we are left with, so they are cancelling each other, I can remove them to find out the net effect. So, situation will be something like this. Here this negative appearing on the surface of dielectric can be effectively drawn this way, and similarly this leftover positive can be drawn this way. I removed all these intermediate parts because their effect for far away point will be 0. So, what happens, you applied some field, that field was E naught, this E naught, and due to that we have got negative charge surface here and we have got positive charge surface here. These are bound charges, right, they are bounded by nucleus, right. So, effectively I can draw that there will be net negative charge here and there will be net positive charge here. So, as you can see, there is net negative charge here and net positive charge here. Because of this charge which got induced, there will be field which will be from positive to negative in this direction, this EP, field due to polarization, right. So, at a time there are two fields, one in this direction and another in this direction. If I ask what is the net field here, net field at this point, so that EP in this direction, sorry, E naught in this direction, this is E naught, and EP in this direction. So, net field will be E net, that is E naught minus EP. Outside dielectric here if I ask what is the field, see this negative charge will produce field towards and this positive charge will field produce away, right. So, there is no effect of this charge on outside point. So, outside point field will be E naught only. So, field here will be E naught, but inside as you can see that will be E naught minus EP, right. And how dielectric constant is defined? Let's see. So, E is equal to the field coming here, net field, this is net, the net field coming here is E naught by K, how that came? Dielectric constant is defined as the field outside divided by field inside. So, the external field you have subjected is E naught and the net field developed inside, the ratio is defined as dielectric constant. So, dielectric constant is defined as external field divided by the net field developed inside the material. So, dielectric constant of material is the ratio of external field to the field net field developed inside the material, right. So, this is the way we define dielectric constant. So, if I say we have some conductor here over here, this material, instead of insulator, if I take some conductor here. So, if I take conductor here, the net field inside, this net field for conductor, net field will be, for conductor as net field is 0. So, if I substitute 0 here, I will get dielectric constant for conductor infinity. So, for conductor we have dielectric constant infinity, but for any insulating material obviously that will be some finite value, right. So, when a dielectric material is subjected to external field, its dipole try to align themselves along the direction of field. In the process, these charges which are appearing on the surface, they are producing net field, they are producing extra field inside, that is given by EP in the diagram. So, net field will be this external minus this which got developed, E naught minus EP. So, the ratio of this external and what we are getting inside, that is called dielectric constant of the medium, right. So, I hope this definition of dielectric constant is clear, and this is also clear why for dielectric, why for a conductor we have got dielectric constant infinity, right, because there is no net field. When there is no net field inside the conductor, if this is replaced by conductor, there is no net field inside the conductor, as this value is 0, this K will be infinity, right. So, there are two types of dipole, two types of dielectric, one is polar, another non-polar, and then we have defined dielectric constant. Now, as you can see that dipoles are trying to align themselves in this direction. So, we defined one more quantity, that is called polarization vector. Polarization vector is the measure of degree of polarization, right, how much material gets polarized when it is subjected to external field. It is defined as dipole moment of unit volume of polarized dielectric, and for a particular molecule, if I assume dipole moment is P and there are n such molecule in the medium per unit volume, then the net dipole moment per unit volume will be n times P, right, and its SI unit is Coulomb per centimeter square. So, if n is the number of atoms or molecules per unit volume and every atom or molecule gets dipole moment P, so net dipole moment per unit volume is n into P, right. This is the way we are defining polarization vector. Now, let us see next one related to dielectric strength. So, as we have just seen, what are dielectric? Dielectrics are insulator which are not allowing charge to flow when subjected to external field. So, if we keep increasing the field, it might be possible that outer shell electron experiences force large enough so that they will come out of the influence of nucleus and they start roaming inside the material, and the material start behaving as conductor, right. So, your insulating material or your dielectric start becoming conductor. So, the minimum value of field which should be subjected to convert that insulator into conductor is called dielectric strength. You can read that if a very high electric field is applied, what happens? The outer shell electron, they start experiencing force and may get detached from their parent atom, right. So, when electron get detached from their parent atom, they can easily roam inside the material and the material start behaving as conductor, right. So, material start behaving as conductor, and this phenomena is known as dielectric breakdown. So, when our dielectric become conductor, that phenomena is known as dielectric breakdown, and whatever be the external field at that time, that is called dielectric strength of the material, right. So, minimum field which can convert our dielectric into conductor, that is called electric dielectric strength. So, dielectric strength of material is that value of minimum field. Now, its unit is volt per meter, right. So, this is the unit of electric field. So, for different material, if I see, for vacuum, no matter whatever field you apply, it will always remain insulator. So, dielectric strength for the vacuum is infinity. Air, as air consists of different molecules, its dielectric strength comes somewhere between 0.1 to 1 kilovolt per millimeter. You can see unit kilovolt per millimeter, right. And similarly, for other materials, I have written dielectric strength, right. Mica, it is coming highest like 160 among all these material what I have written here, 160 to 200 kilovolt per millimeter, 1 millimeter gap, that is very small. This much you have to apply, like 160 into 10 to the power 3 per millimeter to make the mica conducting, right. So, this is very large field, right. This much volt you have to apply, in per millimeter. So, in this small gap, this much big potential difference you have to create to make that mica conducting, and when it just become conducting from insulating, the field at that moment is called electric dielectric strength, right. So, this term is also clear. So, we want our dielectric to always remain insulating, we do not want it to behave as conductor, right. So, this chart gives you idea that you have to apply less than the field written here to keep it insulating. If material is subjected to value of field higher than these values what is written for a particular material, then they start behaving as conductor. So, this is dielectric strength of the material. Now, so we have understood what happens when a dielectric is subjected to external field, right. Now, let us place that dielectric inside capacitor and see what effect it will have over the capacitance of the material. So, if there is no dielectric, without any dielectric, we know the capacitance of the material. So, if this gap is D and the area of plate is A, we know parallel plate capacitance formula epsilon naught A by D, right. So, earlier there was nothing in between the plate. Now, what I am doing, I am placing some insulating material in between. Mica, paper or anything I am placing in between. Then what would be the new capacitance of the arrangement that I want to find out. So, capacitance when filled with the dielectric material, then what would be its capacitance, that we are going to calculate, right. So, till now there was no dielectric, we directly wrote C is equal to epsilon naught A by D. Now some material will be there inside. What would be the capacitance of the material, that we will see. So to find capacitance, I already told you procedure, we will follow the same procedure here. If you remember, capacitance C is equal to charge divided by potential difference V plus minus V minus. So if I get the potential difference, I can find out the capacitance, and we can calculate potential difference. We can calculate potential difference, yesterday I told, with the help of field. So we know this formula, dV is equal to minus E dot dr, right. dV is equal to minus E dot dr. This formula I can use to calculate potential difference. So we know that just outside, if here charge is Q plus Q, and on the plate this charge is minus Q. So negative charge will appear on the surface of this dielectric. So this minus is for the surface of dielectric this side, and this plus is for surface of dielectric this side, right. Diagram is little big, you might be getting confused, that is why I am telling. This negative is on the surface of dielectric this side, and this positive on the surface of dielectric this side, we have just seen, right. Now if I ask what is the field here, so because of this positive charge on the plate of capacitor, I will make it little thick so that it will be more clear to you. Now see, this is our capacitor plate, I hope diagram is now clear. So I was asking what is the field at this particular point. So this positive charge will produce field in this direction, right, and this negative charge appearing on inner surface of this plate, I am talking about this charge, right, that will also be in this direction. So I can see these two will add each other at this particular point, and this negative charge which is appearing on the surface of dielectric this side, and this positive charge, they will produce field in opposite direction. This negative charge will produce field towards, and this positive charge will produce same amount of field in opposite direction, and they will cancel each other. That means the field here just outside is only because of charge on the inner plate of the capacitor. So if here charge is Q and surface area of this plate is A, then field is given by Q upon 2 epsilon naught. So because of this positive charge, Q upon 2 epsilon naught, and because of this negative charge, it will be Q upon 2 epsilon naught, net field will be Q upon A epsilon naught. So here net field coming Q upon A epsilon naught, right, over. And if the dielectric constant of the material is K, the net field coming inside, I am talking about the net, this external will be there, and due to polarization field will be in opposite direction, net field. So at this point net field will be in this direction, E net, and that we know from the definition of dielectric, that is E naught divided by K, right. So inside dielectric field will be by K times, or 1 upon K times the field outside. So the value of field here will be q upon A epsilon naught is the field outside divided by this k. So, I know field here, I know field here, and whatever is the field here, same will be field here. You can see this negative will produce field towards, and this positive charge on the plate will produce field in this direction. So, again q by 2A epsilon naught plus q upon 2A epsilon naught, q upon A epsilon naught. So, field here also q upon A epsilon naught. So, now I have field in this region, I have field in this region, and I have field in this region. Using this field I can get the potential. I hope everything is getting clear. Let the dielectric is placed at some distance x, this total is d, this is x, this thickness is given t, the remaining I can find out from geometry. So, let we are placing the dielectric at distance x, and you know this thickness, only this thickness is t. What would be remaining, that I can find out, right. So, this total is d, this is x, this is t, you can subtract that and you will get d minus, this distance will be d minus x plus t in bracket x plus t. Okay. Now, we are ready to find the potential difference. I am moving from this plate to this plate, right. As you can see, the magnitude of the field is constant. If field is constant, I can directly multiply it to distance to get the potential difference. Field is constant, if field is variable, I need to integrate. As field is constant, I can directly multiply this field to x to get this potential difference. Then I will multiply this field to this distance, I will get this potential difference. Then I will multiply this field to this distance, I will get this potential difference. So, the total potential difference what I am getting plus minus V minus. Okay. Let us see what we are getting. So, field into distance, that is q divided by A epsilon naught into x plus, for this reason, and that is q divided by epsilon naught k. You can see the net field here inside dielectric that I have written, into t, t is the thickness, plus the next term, that is q upon A epsilon naught in bracket d minus x minus t. This way I can write, and we can see that this term and this one, they will get cancelled out, because q upon A epsilon naught outside, when I multiply to minus x, this and this will get cancelled out, right. So, this I can see getting cancelled out by this one. So, we are left with these two terms. So, if I further simplify, then what I am getting is q upon A epsilon naught I will take out, right, in bracket q upon A epsilon naught I have taken out, then this side I can see d minus t, and then this term I can see t by k. Okay. This is the potential difference we have. Once we have the potential difference, we can easily calculate capacitance using this formula, right. So, I can substitute the value of potential difference here and I will get the capacitance. So, capacitance what I am getting is, now this whole term will come in denominator, this q and q will get cancelled out, this A epsilon naught will go up. After simplification I am writing because there is less space. So, what I am getting is T minus D minus T by K, this way. So this is the capacitance of the arrangement. So when nothing was there, that means T was 0. If I substitute T is equal to 0 and 0, then what I am getting? If T is equal to 0, then I am getting C is equal to epsilon naught A by D. That was the formula for capacitor when there was nothing between the two plates. That means we are getting the correct result, right? And when a plate is placed inside, this is the formula. So I hope the whole expression is clear. Now let's see some situation so that this formula will get more clear. So if I say, in the previous case you can see one thing, the formula is not containing any x term. So formula is not having any x term, right? So this x term is not appearing anywhere independent of x. So irrespective wherever you place the dielectric inside, you are going to get the same result. So formula is independent of x, it just depends on the thickness of the plate, and it also depends on dielectric constant of the plate or of dielectric, right? So epsilon naught A in bracket D minus T minus this, this is plus, right? Just make it plus, this is plus, right? So D minus T plus T by K, right? So for this situation, if I ask what is the dielectric constant, the gap between plate is D, and we place dielectric of dielectric constant K is equal to 2 and the thickness is D by 2. What would be the capacitance of the arrangement if I ask? Then we have formula C is equal to A epsilon naught divided by D minus T plus T by K, right? So in that we will substitute the value. Let's see what we are getting. So A epsilon naught divided by D minus T. T is D by 2. So D by 2 I will place here plus this T is again D by 2 and the value of K given is 2. Place 2 here. If you simplify, then A epsilon naught, this D I will take out, and this is 1 minus 1 by 2, that will be plus 1 by 2. So this term will be plus 1 by 2 and this is 1 by 4. If I simplify, multiply and divide by 2, this will become 2 and 4 will go up, and what we are getting 4A epsilon naught divided by this we are getting 3D. So this is the capacitance of the arrangement, right? I may have a situation where multiple slabs are present. So I hope formula is clear. So if multiple slabs are there, of different dielectric constant, multiple slabs are there. If this is the situation, then how to write the dielectric constant, how to write the capacitance of the arrangement? So, I have assumed, say this is having dielectric constant K1 and its thickness is T1. This is K2, its thickness is T2. This is Kn and its thickness is Tn. So, the space between the capacitor is filled by n dielectric slabs this way, and I want to find out the capacitance. The same formula, epsilon naught A divided by d minus T plus T divided by K. What I will do? I will put sigma. So, here I will add sigma, here I will add sigma I, where I is equal to 1 to n, I is equal to 1 to n. The whole formula I can modify and I will get the capacitance for such type of system. So, when there are so many slabs, for every slab we have to write. So, here actually this is epsilon naught A divided by d minus T1, T2 up to Tn I will write, then I will put plus, then I will write T1 divided by K1 plus T2 divided by K2, so on up to Tn divided by Kn. So, I can write the capacitance of this arrangement, this just substitute the value of dielectric constant and thickness in the formula, you will get the capacitance of this arrangement. So, I hope it is also clear. Now, what if I have, instead of a dielectric slab, I have a conducting slab placed this way? Let us see. So, this point is clear, I will erase it. Now, what I am doing, I am placing a conducting slab. So, this gap is D and a conducting slab of gap say D by 4 is placed. Now, what would be the capacitance? As we know, the dielectric constant for conductor is infinity. I can use the same formula, there I will place the value of K as infinity. So, C is equal to, formula was epsilon naught A divided by T minus D, D minus T plus T divided by K. So, C is equal to epsilon naught A divided by D minus, in place of T I can write D by 4. So, here I will write D by 4 and plus this I will write D by 4 and then K infinity, if I substitute here, then this term will become 0. That means capacitance here will become epsilon naught A divided by D minus D by 4. Look at the formula, it says that this much space will not be the part of the capacitance. If you see this formula, D minus D by 4 is this space only which is left over. So, our conductor was occupying this space of thickness D by 4, that is of no use, only this and this will behave as capacitor, this space and this space will behave as capacitor. So, effectively we are getting D minus D by 4 over here, right. So, even if conductors are given, we can apply the same formula with K is equal to infinity, right. Now, if I give you a little different situation, so I hope this whole thing is clear. Now, we will move to next one. So, these are two conducting plates of capacitor and I inserted a structure in between these two of say this shape. And this is made up of conductor, this whole thing is conductor. And let this distance is d by 2 and this whole gap is d, and I ask the same question, what is the capacitance of the arrangement. Now, as you can see that this space will be utilized as a capacitor, similarly this space will be utilized as a capacitor, but here this space cannot be used as capacitor, right, because whatever be the potential here, same will be potential here, there will not be any electric field here, there will not be any electric field here. So, here there will be electric field. If I give positive charge to this one and I give negative charge to this one, what will happen? Facing surface will have equal and opposite charge. So, this surface will have minus q charge and this surface will have plus q charge, right, because it was electrically neutral. So, total charge has to be 0. Here this will have plus q, minus q, and this will have plus q. So, if you look at the field pattern, then field lines will be from positive to negative, from positive to negative, and here field lines will be again from positive to negative. So, field lines will be like this. So, here I can see that this space is behaving as capacitor and this space is behaving as capacitor. This whole conductor will be at the same potential. If this whole conductor is at the same potential, this point and this point are at the same potential, there should not be electric field in this region. So, there is no electric field in this region, there is no electric field in this region, and inside the conductor also there is no field. So, there is no field from this point to this point, everywhere it will be 0. Now, how to use the formula? As I can see, this space is not being utilized. I can consider this as the whole thing as a single slab of thickness d by 2. I can substitute d by 2 here. because everywhere field is 0. So, I can consider this as whole slab, a single slab of thickness d by 2. So, C is equal to epsilon naught A. In place of T, I am going to write d by 2 and then plus this is again d by 2 and K is equal to infinity, right. So, this will become 0 and epsilon naught A divided by only d by 2 is coming. So, this is the capacitance of the given arrangement. So, sometime it might not be in the form of a full or complete slab. In those cases we have to analyze little bit what space is behaving as capacitor, what is not behaving as capacitor. After deciding that, we can substitute the value in the formula and we can get the value of capacitance. So, till now we have seen few examples, so that this formula epsilon naught A divided by d minus T plus K is clear, right. Or we may have a situation where there is a combination of dielectric as well as conductor, right. So, let us see one more example. So, I am taking one dielectric slab of d by 4 and one conducting slab so this one I have taken conducting and this one I am taking dielectric. So, conducting means K is equal to infinity for this one and thickness of this one say d by 4 and this one is K is equal to 3, right, and thickness is d by 4, this total is d. Now, I am interested in calculating the capacitance of this arrangement. So, again we have to just place the value in the formula. This is the formula we have and now I will write all these values epsilon naught A divided by d minus, for this slab thickness is d by 4 and another slab thickness is d by 4, right. So, this term over, right, this I have written here. Now, I am writing second term. So, for this slab I will write thickness d by 4 and the dielectric constant here as T is equal to, K is equal to 3 plus the next one. The next one is conducting plate d by 4 and its capacitance is infinity, right. So, this way I can write. As you can see, this term will become 0. We are left with epsilon naught A divided by this d by 4 and d by 4 will give you d by 2. So, that d by 2 and this d will give you d by 2 only. So, this whole term will give you d by 2 and then here we are left with d by 12. So, you multiply divide by 6, here I can see 7 and then 12. So, 12 epsilon naught A divided by 7 d. This is the capacitance of the arrangement, right. So, in between the plates only dielectrics might be given, only conductor might be given or the combination of dielectric and conductor is given. So, this is the only formula we have. We need to substitute the value and we will get the result, right. So, if I draw the circuit again or if I draw the diagram again, then this charge will produce field at this particular point in this direction, and it is q upon 2 epsilon naught. Similarly, this charge will produce field at this point q upon 2 epsilon naught, net field because of these two, net field is q upon a epsilon naught, right. And field due to the charge appearing on the surface of dielectric. So, dielectric I am drawing this way. So, here charge is Qp, charge appearing due to polarization, right. So, this negative charge will have field in this direction, this negative charge will have field in this direction, and this positive charge will also have field in this direction. How much this negative charge will produce at this particular point, that is Qp upon 2 epsilon naught. So, Qp upon 2 epsilon naught because of this negative charge, and Qp upon 2 a epsilon naught because of this positive charge. So, net field at this particular point is Qp divided by a epsilon naught. So, because of the polarization charge due to polarization, field here is Qp upon a epsilon naught. Because of this charge appearing on the surface of capacitor plates, this is q upon a epsilon naught. So, the net field will be, you need to subtract this to this. So, q upon a epsilon naught minus Qp upon a epsilon naught will be the net field there. And we know that this net field is E naught by k. We know from the definition of dielectric constant that the field here is by k of field here. So, if field here is E naught, then the field here will be E naught by k. So, in place of this net field, I can also write E naught by k. And what is E naught? This E naught is q upon a epsilon naught, because this Qp cannot produce the field outside, only this q and this minus q will produce the field here, and plus q will produce q upon a 2a epsilon naught, and minus q will produce q upon 2 epsilon naught. So, net field here will be q upon a epsilon naught, right. So, inside I can write field, if I substitute this value over here, this value over here. So, by k I need to write q by k a epsilon naught, q by k a epsilon naught must be equal to this term. Now, this a epsilon naught and this a epsilon naught gets cancelled out, and I can rearrange this term to get the value of Qp. So, the value of Qp what we are getting is q in bracket 1 minus 1 upon k. We are getting only magnitude because sign we have already considered, right. So, this surface charge will be minus and this surface charge will be plus, and the magnitude of that charge will be q 1 minus 1 upon k. And we know that if this dielectric is replaced by conductor, then facing surfaces have equal and opposite charge. So, let us check we are getting the same result or not. If I substitute k is equal to infinity, then this term will become 0 and you are getting Qp is equal to q. So, for conductor, facing surfaces will have equal and opposite charge, but if dielectric is placed in front of this conducting surface, this plate, then the charge appearing on the surface of dielectric, that is given by this formula, right. So, Qp is equal to q in bracket 1 minus 1 upon k. So, we talk about effect of dielectric when placed inside capacitor. We also discuss how to find out the capacitance for such arrangements, and just now we have seen how much would be the charge appearing on the wall of dielectric, right. Formula is 1 minus 1 upon k times the charge, right. So, all these basic points we have discussed. Now let us move to next one. Effect of dielectric insertion in a capacitor. So when I insert dielectric inside capacitor, what happens to the parameter involved in the situation? We want to see what happens to the capacitance, what happens to the field inside, what happens to the energy, what happens to the charge. So there are two possibilities. First one is like you have a charge capacitor, you connected initially capacitor to the battery, it got charged, and then you remove the battery, right, and then you are inserting the capacitor into it. This is first situation. And the second one is you insert the battery, you insert the dielectric when battery remain connected through the capacitor. So these are the two situations. So we will see both the situation one by one, right. So first situation is I have got isolated capacitor. So after charging, cell is removed. So we charge the capacitor and cell is removed. So once we charge the capacitor, there will be charge appearing on the inner surface this way. This is minus Q and this one is plus Q. Okay. Now we are going to insert dielectric. So dielectric is inserted into capacitor, right. What is the formula for capacitance? We have seen C is equal to epsilon naught A divided by D minus T minus or plus T by K. If I say that capacitor is occupying full space, capacitor is fully filling the space between the capacitor, then this value will be D and this value will also be D. So if this value is D, this D and this D will get cancelled out, here D, and the expression will become epsilon naught A by D into K. So capacitance of the system where dielectric is completely filling the space is K times A epsilon naught by D, and the value of dielectric constant for vacuum is 1, and as we start moving from vacuum towards conductor, the value reaches to infinity. So the value of K is always K is always greater than equal to 1, right. So the value of K is always greater than 1. If greater than or equal to 1, that means once dielectric slab is inserted, its capacitance got increased. Earlier when no dielectric was there, then formula was epsilon naught A by D. So this was the formula earlier. So initially capacitance was this, and now the capacitance has become this K times A epsilon naught by D. So you can see that capacitance got increased, right. So capacitance will get increase, that we understood, and using the formula we derived, we got this result K A epsilon naught by D. Now so let us look at all the parameter, what happens to the charge, what happens to capacitance, what happens to the field, and potential difference and energy stored. So, charge first, as it is isolated, no battery is connected, no battery is connected. Look at this one, this is isolated, no battery is connected, and then we are inserting dielectric, then the charge will remain same because there is no source which can deliver the charge. So, the charge is not going to change when we insert the dielectric. So, charge remains same. What happens to the capacitance? Just now we have seen that capacitance will become K times, right. So, capacitance increases and it becomes K times. What happens to the electric field and the potential difference? Let us first talk about the potential difference, then we talk about the field. Potential difference, Q is equal to CV, Q is equal to CV. Charge is constant, this quantity is constant because there is no source which can deliver the charge. When you inserted dielectric, then capacitance got increased, it now become K times. So, capacitance is getting increased, the product has to be constant. So, for that potential must get decreased. So, the potential must get decreased, right. So, this potential difference must get decreased, and E is equal to, or dV is equal to E dot dr, right. With minus sign. So, here this is getting decrease, potential is getting decrease. The gap here is d only, from this plate to this plate you have to move through distance d. So, this is d only, this is getting decreased, this is getting decreased, this is same, this is same. So, this must get decreased, right. So, field must get decreased and potential must get decreased, right. Field must get decreased and potential must get decreased. You can extend another logic. See, here field is E naught and the field here will become E naught by K, right. So, this E naught is not going to change because that E naught is Q upon A epsilon naught. As charge is not changing, the field here is not changing, field here is not changing, but inside it will become E naught by K. So, field here will become less than the previous value. Earlier when dielectric was not there, field everywhere was E naught. Now, when dielectric come into picture, then the field inside the dielectric become E naught by K. So, field inside the dielectric is E naught by K, which is less than the previous value. So, field got decreased, potential got decreased, energy is stored. Energy is stored, I can apply any of the three formula like half Q square by C, half CV square or half Q into V, right. So, half Q square by C if I apply, charge is same, charge is not changing, capacitance is increasing, energy must decrease, capacitance is becoming K times, the energy must get decrease, right. So, energy is stored inside the capacitor. Let us see, this is complete energy stored, this is capacitance is increasing, energy is decreasing, sorry, this is so. Later we will see that moving it inside we need to do some work. Obviously, if you are doing some work, then energy will get altered, right. So, here it is actually energy decreases. From the expression also you can see U is equal to half Q square by C, and when you insert dielectric then capacitance will get increased, it will become K times C. If it is becoming K times C, then whole value will get decreased. So, energy decreases, right. So, this whole thing is clear when we have isolated capacitor. Now, if I keep the battery connected to the capacitor, what happens to all these parameters we just discussed, right. So, now this is inserted. Earlier, if here charge was plus Q and here charge is minus Q, and as soon as I insert this one, the capacitance of the whole arrangement which was earlier C, the capacitance of the whole arrangement which was earlier C, then as I insert the plate, insert the dielectric, the capacitance will immediately get increased, capacitance will become K times. If capacitance is K times, then we know Q is equal to CV. Here voltage is fixed, voltage is constant, right. So, this quantity is constant in this case, constant. If this quantity is constant and we are inserting the slab, if C get increase, the Q must get increase. If this is becoming K times, charge must become K times. So, what happens? Battery will deliver some extra charge, and here charge will become Q times. So, when dielectric goes inside, capacitance of the arrangement get increase as potential remains constant, capacitance is increasing, charge must increase, charge will also become K times, right. So, charge increases, capacitance increases, field inside. Now, you can see field is again dV is equal to E dot dr, right. As source remains connected, potential is constant. If potential is constant, potential is not changing, this gap is also not changing, this is also D, this gap is same, then field must be same. So, the field will remain same, right, and the potential difference that also remains same, the potential difference here will be V only. The last one, the energy stored. So, for energy stored, I can now use half CV square, because in this case potential is constant, that is why I am using this formula. In previous case charge was constant, that is why I use the formula half Q square by C. Now, in this case potential is constant, that is why I am using half CV square. So, potential is constant, capacitance is increasing, energy must increase. So, energy must increase and it will become K times of the initial value, right. So, this is the effect when a charge isolated capacitor we are introducing dielectric, or a capacitor that remains connected to the battery and we are inserting dielectric, right. So, I hope all these points are clear. So, this is it in today's session. Download the assignment and start working on this topic and post your doubt if you have any doubt, right. So, I hope you enjoyed today's class. So, tomorrow we will talk more about circuits which involves the movement of dielectric, and we will see some numericals based on that, right. So, thanks for watching.